Okay, so today is the last lecture on compressed sensing. We're going to see a different way of showing exact recovery, right? And so let's recall that we have, right, X, a vector that says sparse, right? It lives in n dimensions, big N, and, right, we have measurements of the type AX equals Y, where Y lives in m dimensions, right, with m smaller than n. Right, and the way we're going to recover the vector x was via L1 minimization, right? So this is what we saw last time through the null space property, right? By solving this problem, such that AZ equals Y. Okay, and then we showed that if A satisfies the null space property, then the only unique solution is X, and we used Gordon to understand what is it that it does satisfy the null space property. Now I'm going to show you a slightly different way. Okay, and I'll omit some details, but all the details are in the notes. You can see them there. But remember that, right? What we said, that this really is the same as a linear program, right? Where if we take W plus to be the positive part of X and W minus to be the negative part of X, then it's really the same thing as minimizing one transpose W plus W minus, right? Such that, right, these had to be positive, these had to be positive as well. And, right, because this was the positive and the negative part, then the vector is equal to the difference. Right, so this had to be equal to Y, right? And this was a linear program, right? This was some linear program, corresponds to L1 minimization. They're completely equivalent, right? We can call this L1, but they're completely equivalent. This is what we saw. Okay, so now what we can do is we can prove that X is the optimal solution to this through duality, just like how we did for the stochastic block model and community detection. Right, so we can derive the dual using this game theoretical approach as well. This is done in the notes here. I'll just write what the dual is. Right, so the dual of this, and then we'll check weak duality, is of course, if this is min, it will be max, U transpose Y, right, subject to the constraints that minus 1, U transpose A. Right, so that subject to the constraint, I mean, here I can write, usually constraints are written with a vertical vector. So let me write ATU. It's the same, right? Where all the entries of this are between minus 1 and 1. Right, so this is definitely a linear program and is dual to that one, okay? Can we see that it's dual to that one? Well, I mean, you can derive the whole, like, exactly how we did in the stochastic block model, right? The whole game theoretical thing of the primal player and the dual player and so on. And we'll have weak duality in the sense that the value of this is always smaller or equal than the value of that. And in linear programming, we also always have strong duality, right? It's a bit harder to show strong duality, but it is also holds. But proving weak duality is actually quite easy, right? Because to prove weak duality, we just need, in order to prove weak duality, we just need to put the variables together. It's exactly like how we did for the stochastic block model, right? We take 1 transpose minus a U transpose A, right, times W plus, right? This variable is for sure positive everywhere, right? Because of this constraint. And this value is also positive everywhere. So for sure, this is positive, right? And we can do exactly the same with, right, with plus. Right, again, this random variable is positive, right? It's a vector of positive entry. So the inner product is this, right? There's a transpose here. So this is the inner product with the vector 1 plus A transpose U is also positive. So this is for sure positive. But now if we work this out what this is, right? What is this? I'll switch to another pen so that it doesn't look like it's part of the program, right? What is this? This will be 1 transpose W plus 1 transpose W minus. So 1 transpose W plus W minus. Right, plus, right, then what we have, or let me do minus actually, right, so that this minus from here, right, minus, and then what we have U transpose A, right, and then there's W plus, right, because of this minus, and the W minus, but I need to put a minus because here is a plus. But this is exactly X, right? And so this is exactly Y, right? So then this term, right? This term here is just U transpose Y. So in particular, this 1 transpose times this minus U transpose Y is bigger or equal than 0, right? This is equal to the objective value for the primal, for the original LP, minus the objective value for the dual. Right, so this shows you weak duality, right? Because if these are positive, then this one is always bigger than that one. Okay, so we already have, with this, we have the weak duality, and then the fact that this is always bigger or equal than that. But now, in order for us to show that X, right, that X equals to W plus minus W minus is the optimal solution to this, right? We want to show that if we take X W plus minus W minus, right, where it's just the positive part and the negative part is really the optimal solution to this, all we have to do is to find the U that for which these values match, right? But because of complementary slackness, we know, right? Or just by looking at this formula, we know that for this to match, then this really needs to be 0. So which means that for all the entries, either the entry here is 0 or the entry here is 0. Right? So for all I, either U transpose A, right? So maybe I should write it like this, right? So for all entry I, if Wi plus is bigger than 0, so if X is positive there, then U transpose A entry I really needs to be 1, right? And the same thing here, right? If W minus I is positive, then this needs to be exactly minus 1. So basically what we get from here, right? So let me, right, we won't need the program anymore. Right, what we get from here, complementary slackness tells us that if for them to be an equal pair, right, for U to be actually a dual certificate, right, for U to be so that you get, you actually get the same value, we need for sure that U transpose A is 1 whenever X is positive and it's minus 1 whenever X is negative. So if we call S the support of X, right? This was very much like how we had it to be, right? Those two matrices in the stochastic block model example that the matrices had their trace had to be 0, right? If we take the support of X to be X, then what we need really is that A transpose U, say U transpose A in S, right? The entry is S of this. Right, I mean, let's go back to vertical vectors, right? This is an horizontal vector, let's just make vertical vectors, right? So I'll just take the transpose. ATU, right? There's entries S of this, right? That this is equal to the sine of X, right? Because if this is the case, right, then, right, if X is positive, then this means that W plus is positive at that entry. In particular, what that means is that, right, ATU S needs to be 1, and so this becomes 0, and so it doesn't violate complementary slackness. So we know for sure that the U that we're looking for needs to satisfy this, right? Complementary slackness already tells us where to look for. Also, now if ATU outside of S is actually in absolute value, right? Say an infinity norm, all the entries are actually strictly smaller than 1, then what does this mean? It means that, right, if this is the case, then for sure it satisfies the constraints, right? Because, right, it satisfies the constraints because ATU S equals the sine, right? All these products will be 0, so the values are the same. Moreover, because it satisfies the constraints not just with big or equal, but strictly, then it must be that if there were even potentially, okay, so this is a certificate in the sense that if U satisfies this, then because of this identity, then the values are the same. Because weak duality always holds, we can never have something in the primal that's better, right? So that's clear. But we could potentially have something in the primal that's just as good, meaning there could be another vector Z that's just as, has an L1 norm that's just the same as X. And so that would be no good, right? Because then if I were to optimize, I wouldn't know, if I get two solutions, I wouldn't know which one would be the right one, which one corresponds to the image I want to see. But if it's smaller than one, then it must be, right, because it's smaller than one, because of complementary slackness, it must be that the optimal W is 0 in that entry, which means that if this holds, then even if there is another optimal solution, it must have the same support as X, right? So if we ask that AS is injective, right, what does this mean? That it doesn't send any two vectors with that particular sparsity pattern to the same one, which is very expected if M is bigger than S, right? I mean, this means like if I were to tell you the sparsity pattern, you would be able to solve the problem. That's very reasonable. So if this is the case, right, and if we find U that satisfies this, then it must be that X is the optimal solution, right? And so this is all is done like more carefully in the notes, but it should be clear that duality allows us to immediately get a theorem. Right, so we immediately get a theorem that, so theorem, okay, take L1 optimization, take S to be the support of X, right, if there exists a vector U, right, such that ATU, right, at S is equal to the sign of X at S, of course, and ATU S complement is strictly smaller than 1, and A, when just restricted to that support, is injective, right? Then we know from here, right, then X is the unique optimum of L1. Okay, and so this is another approach to getting guarantees for recovery with L1 optimization, right? And doesn't use necessarily the null space property or the restricted symmetry property, right? Is a different way, and this is better for some applications. Like this is ideas like this are used for example, super resolution and so on, right? I'm showing a few different ways of obtaining these arguments, of arguing that recovery in the sense, so that if you have an application you're interested in, you can try a few different ones. But now, in order for us to actually show this, we need to prove the existence of such a vector U. How do we do this? Right? How do we prove the existence of a vector U? Right? How to find U? And when we did it in the community detection in the stochastic block model, basically there everything was set for us, right? We had all the constraints that we know needed to be satisfied. The linear one just told us immediately what we needed, right? But here is not clear that these constraints by itself, the equality constraints, tells us everything. Right, but because we know, there'll be potentially many vectors U that will satisfy these equality constraints, right? But that doesn't mean necessarily that all of them will satisfy this infinity norm constraint. But what we can do, right? So here we make a sort of a guess, right? Before in the stochastic block model stuff, we didn't have to make a guess, right? The equality constraints told us everything we needed to know. Here we'll make a guess. And so the idea is that we'll pick a guess that's easy to analyze. Right? And we'll pick the guess that matches the equality constraints. And because we know that we want this vector to be small, right? We somehow want U to be small. We'll just pick this. We'll try to satisfy these equality constraints and try to minimize the L2 norm of U, right? Because this is something that we know how to do, right? We understand because of the pseudo inverses and so on, and least squares. So we'll force AT, right? So another way to write this is ATS U, right? We'll force this to be the sign of XS and do least squares. Okay, so we'll take, we'll take the we'll take the vector u that has the smallest L2 norm of all the vectors that satisfies that. So, right, so in particular, our guess is given by, switch pens. Our guess will be given simply by the pseudo inverse. Right, just take the Moore-Penrose inverse, sine of xs. Okay, where of course this is just a pseudo inverse. Right. We take this is simply as right, the so-called Moore-Penrose pseudo inverse. And so now this is a reasonable guess. Right, and it turns out that this guess works quite well. And in particular, now we can change our theorem, right? Now instead of a theorem, we have a corollarium. Let me see if I can, maybe I'll do it with another pen. Okay. So now we can write a corollarium, right, of this original theorem, right? Corollarium, S equals support. If now we don't need to say exist U. We just need to say that, well, we still need that AS is injective, sure. And we need that an infinity norm of that is right, all we need is that the infinity norm of that is smaller or equal than 1, because the way we solved it, of course, it will satisfy these equality constraints. And so the S is support of this. And now our condition is simply this condition, A transpose is complement, and now we just have to write this, AS. Right, and if AS is not injective, right, there would be issues here, but okay, yes, injective is part of this constraint. Sine. Okay, so now it's nothing about there exists or anything like this, right? The theorem now simply reads, let S be the support of X. If this norm is smaller than 1 and AS is injective, I mean, if AS is not injective, you're in trouble doing this. And AS is injective, then X is the unique optimum of L1. And of course, you know, if AS is not injective, then it's sort of hopeless, right? Because even if you knew the support, you would still have trouble. Right, and so now the question is, how do we prove that this actually happens with high probability? And so this can be done essentially with concentration inequalities. Right, so I'll skip here the proof of that, but this is in the notes. After setting this up, it's actually quite easy, right? Because you can control the spectral norm of these random matrices if A is Gaussian, for example, right? So now we can ask, okay, does this happen for Gaussian matrices a lot? You can control the eigenvalues of these Gaussian matrices, and then the infinity norm is just, you know, the maximum over a bunch of things, and you can do union bound. Okay, so you can take a look at the notes for the proof of this, right? But now it's sort of an exercise in, it's an exercise in concentration inequalities, right, and union bounds and so on. Okay, so this is yet another way. So basically we saw, or we alluded to 4 different ways. One was the fact that the restricted isometry property implied the null space property. Another was this. Another was trying to look at the Gaussian width of the descent cones for just one point. And another was what we did with the null space property, where the null space property is about something not intersecting with the kernel, and we just look for Gordon's theorem to tell us when is it that there won't be an intersection. Okay, so now I'll talk a little bit about building deterministic RIP matrices, or matrices that are good for compressed sensing. And I'll try to describe where the square root bottleneck is coming from. This is a fascinating source of open problems, by the way. So many open problems are in the notes, and I'll sort of mention a few. Right, I mean, many open problems in this area are related to, what if I don't want the matrix A to be Gaussian? What if I want it to be, right? I can't say, if I'm making an MRI machine, the way the measurements are taken, they have physical constraints due to the technology, right? I can't just take Gaussian matrices. There's only certain types of matrices. Basically, the machine rotates, and you can just, right? So rows of the measurement matrix are just different rotations of the machine, right? So I can't just put Gaussian entries. So maybe what I can do is draw random rotations of the MRI machine or something. Even that would be tricky, but let's say, right? And now I can ask, does that random distribution, is it random enough, right? And so one thing you can do is take, for example, random rows of the Fourier transform and study that. And exactly how many rows you need is still, there's a lot of very interesting open questions related to that still, right? And there's many open questions related to many other constructions where we know a lot about if the constructions are random. We still don't know exactly what the right answer is for how many rows we need. But for deterministic ones, we really know very little. Okay, so let me just try to sort of give an intuition of why it's so difficult, right? So what we want is if X, right? So we have X as sparse, right? And so what we want is a matrix that satisfies this for all X as sparse. Okay, but now let's look at the square of this a bit better, right? So what is this? This is 1 minus delta, right? X transpose X. Okay, let me make another look silly change, but let me put an identity here. Of course, nothing changed. Right here we get X transpose A X, right? Because it's this transpose times this. Right, but written this way, it's clear I can just subtract this on the other side and get 1 minus, right? I'm just going to take away the 1, right? And I'm going to send it to the, okay, maybe I'll do this, maybe I should do this slightly different. Let's say, right, I have X transpose identity X, right, minus delta, say X transpose X. Right, this is clearly the same thing, right? Because this is X transpose X minus delta X transpose X. It's exactly the same as that. But I want to do it this way so that I can then move the, okay, now I can move the identity in. And I can even move the X transpose X underneath, right? Divide. So I get X transpose A minus identity X divided by X transpose X, right? I move first the identity, smaller equal than delta. Right? So if you think about this, right, this is saying that the spectral norm of A transpose A minus identity is smaller or equal than delta, right? Because the maximum over all X's here, this needs to be smaller or equal than delta. Now, of course, it's not quite that, right? Because X needs to be sparse. Because X is at most 0, S non-zero entries, really it only picks up an S by S submatrix of this, of A transpose A minus identity, right? So really this is equivalent to just saying that for all S subset of N, right, such that the size is S, we just need, you know, the, right now this identity becomes an identity, of course, S by S, right? Taking the S by S submatrix here or taking just S columns on A is the same thing, but we need the spectral norm of this to be smaller or equal than delta, right? Because if the spectral norm of this is smaller or equal than delta, then if the support of X is S, then for sure this needs to be true, right? Because X will only see the S columns of A, right? So remember that this is an S by S matrix, while here it wasn't, right? Here it was just a general N by N matrix. Okay, so essentially what we need, right? What we need is for every subset of S columns of A to behave very much, right? They're almost an isometry, right? Its Graham matrix should behave like an identity. Okay, but then, right? So then what's one way that we can do this? So we can try to make this small by just making the columns. Okay, so let's now write A in its columns being like this. Right, there where these vectors are vectors in Rm. Okay, these are not the measurements, right? The measurements are the rows, but let's write it like this, right? Because then by hitting with a sparse vector, we're getting a sparse linear combination of these vectors, right? Let's say that we ask these vectors, right? The vectors ui, its norm to be 1. If we ask that, then the diagonal here, right? What is the diagonal here? The diagonal here will just pick up ui transpose ui. So the diagonal here will be 1. So when I subtract by the identity, the diagonal will be 0. right? And so at least in the diagonal, we're getting exactly the right thing. But now we want to make this matrices as small as possible. One thing that we could ask is to try to make all the entries of this matrix very small. The entries of this matrix are, of course, the inner products of the different vectors, right? So we can ask Qi, Uj to be small, right? For I different than J. Okay, so if we ask for that, right, we can ask, for example, that the maximum for all I different than J of the inner product Ui, Uj to be equal to some mu, and try to make mu as small as possible. This is known as coherence of the system of vectors Ui, Uj. Now, if there is a certain coherence, or incoherence is when this is small, right? But mu will be the coherence parameter. Then for a certain coherence, right, as we saw when we talked about, when we talked about these things like page rank and so on, we used the Gershgorin circle theorem. The Gershgorin circle theorem just tells us that the eigenvalues of this, right, are within these disks. They have centers at the diagonal, and this radius is the sum of the absolute values of the off-diagonal entries in a row or a column. Because the diagonal elements here are zero, Gershgorin, right, Gershgorin circle theorem tells us that all the eigenvalues, all these eigenvalues are small or equal. They're small or equal than what? They're small or equal than the sum of the absolute values of all the entries of the diagonal, because the diagonal is zero. But all those entries, they're small or equal than mu. And how many are there of them? There's s minus 1, right? So this is small or equal than s minus 1 mu. Okay, so we have in particular that a matrix, like if we have the matrix A is RIP for S and S minus 1 mu. And doing this type of construction deterministically, it turns out that it's not so hard, right? Because we're very good at building vectors and checking if they have small inner products or not. Okay? And in particular, we can now ask, okay, what if the vectors are random, right? What if I draw random vectors? What's the typical coherence that I see, right? And the vectors to have norm 1, let's say they're Gaussian vectors that typically have norm 1, then their inner product will be something like 1 over the square root of their dimension, so 1 over square root m. So at least for random vectors, we expect mu to be something like 1 over square root m. Erase this. Right, for random vectors, we expect mu to be something like 1 over square root of m. Right, so this is the max, maybe an extra log factor, right? But I'm not worrying too much about the extra log factor for now. Okay. So if you think about it, this is already bad news, right? Because if we're going to use this tool for random constructions, all it would give, right? Because we need this to be, say, below a third, right? We would need s minus 1 over root m to be, say, smaller than a third. Right? It would mean that we would only be able to hand sparsity that's around square root of the number of measurements, right? The so-called square root bottleneck. And here you're sort of already seeing it. But somehow what's happening is that, the random constructors are much better than this bound, right? Because Gershgorin can be potentially very pessimistic. If all the entries in the row have flipping signs, plus and minus, it could be a lot of cancellations that we're not seeing. But another approach, right, is to say, okay, that's fine. I don't really care about doing random with this type of proof. I want to try to build vectors U that are much, much better than this. Right? And in general, I mean, this type of constructions is almost never better than what you can do randomly. And indeed, there is something known as the Welsh bound. The Welsh bound is a lower bound on the minimum coherence, on the maximum coherence. So a lower bound on, right, the maximum coherence. And it says that mu is bigger than n minus m over m n minus 1. Right, so essentially, if n is much bigger than m, I mean, these numbers will be roughly the same, and so this is basically behaves like 1 over square root m. And so you can never beat random by very much. And so if you're going to use this type of tool, then you're stuck at the square root bottleneck. You can only handle sparsity that's around square root of the number of measurements. When two random constructions do close to the, up to maybe some log factors, but get to linear on the number of measurements. Okay? And so now in order to try to improve over this, you really need to take into account the fact that even though the absolute values may be mu, right? Some are positive, some are negative, and there'll be a lot of cancellations. This seems incredibly hard to do. Right? I mean, you could also try to take advantage of the fact that maybe, maybe one of them uses large and the others are small, but actually when you achieve this, all of the inner products have absolute value mu. And this is known as an equiangular tight frame. They're very important objects also for quantum mechanics and so on. And there's many conjectures about their, like many really fascinating open problems about their existence. Right? Now I can ask, if I go into here, I can ask all sorts of fascinating questions of the style, okay, so in given dimensions and given vectors, can I put vectors, can I actually achieve the Welsh bound? Or for which dimensions can the Welsh bound be achieved, and so on and so forth. And this, this are actually very interesting questions related to quantum mechanics and so-called SIG POVMs and equiangular tight frames and so on. I reference some of the open problems in this area in the lecture notes. And so there is an improvement over these constructions that is basically a result that exploits this type of cancellations to some extent and gets something like square root m plus just a little bit, right? And this is so far the best node. And we have no idea how to get, say, m to the 0.6. Okay, and lots of references to these and the other open problems and so on are in these like 10 lectures and 42 open problems lecture notes in my webpage. Okay, right? Thank you all for listening. Thanks very much.